Good morning, students. Today we shall be discussing about the F block elements. We know the position of F block elements. They are right at the bottom of the periodic table and are also known as inner transition elements. And we know that in the inner transition elements, that is the F block elements, the additional electron, they will enter in n-2 F orbitals. Okay. Now let us see the position of the periodic table. We will see that at the bottom of the periodic table there will be two series. And the first one will be the Lanthanide series and the next one will be the Actinide series. Now in Lanthanide series you will see that the atomic number, the elements from atomic number 58 to 71, that is starting from cerium to lutetium, you will find the Lanthanide series. Then actinoid you will find from the atomic number 90 to 103. So we have the elements between thorium and lawrencium. Now let us study about the lanthanoids. So these lanthanoids, they are very reactive elements, and that is the reason why they are not found in the free state. And most minerals for the lighter lanthanoids, that is monazite, then cerites and orthite, and for heavier alkaloids we have the gadolinite and the granotite. So these are some important minerals which are found in the lanthanoids. Okay. Now let us see the general electronic configuration for the lanthanoids. The general electronic configuration will be given as xenon 4f1 to 14, 5s2, 5p6, 5d0 to 1, 6s2. So this is the general electronic configuration for the elements belonging to the lanthanoid series. Now let us just have a view of the series. So we have from the atomic number 58, that is cerium, to we have lutetium. So here we have 58 to 71. All the elements from 58 to 71 belong to the lanthanoid series. And of these we will find that gadolinium will have 4f7 electrons, okay, in their outermost shell. So this is highly stable, we can say. And another one will be, you see, lutetium, which will have 4f14. Okay, that means the f orbital is completely filled. Okay. Now it is to be noted that filling of 4f orbitals in the atoms is not regular. A 5d electron appears in the gadolinium, Z equals to 64, that's the atomic number, with an electronic configuration 4f7, 5d1, 6s2. This is because 4f and 5d electrons are at about the same potential energy, and hence the atoms have a tendency to retain the stable half configuration. On the other hand, the filling of f orbitals is regular in tripositive ions. So all the tripositive ions of this lanthanoid series, the filling of the f orbitals will be regular. After losing outer electrons, the f orbitals shrink in size and become more stable. Then Pm is the only synthetic radioactive in the lanthanoid series. Okay. Then let us go for the oxidation states. Now here you will find the oxidation states +2 and +4 and +3 also. But +3 here will be the most common oxidation state. Now except cerium and terbium, it will have oxidation state of +4 also. And ytterbium and europium will also have the oxidation state of +2. Then let us see about the magnetic properties. In tripositive lanthanoid ions, that means all tripositive ions, the number of unpaired electrons regularly increases from lanthanum to gadolinium, that is from 0 to 7, and then continuously decreases up to lutetium, that is means from 7 to 0. Then lanthanum and lutetium ions are diamagnetic, while all other tripositive lanthanoid ions are paramagnetic. So obviously it is diamagnetic, means they are either completely filled, isn't it? There will be no unpaired electrons. And while the other tripositive lanthanoid ions, they will be paramagnetic because they will have incompletely filled orbitals, f orbitals. Except neodymium is the most paramagnetic lanthanoid. So keep that in mind. Then Ce+4 and Yb2+. In this oxidation state, these lanthanoid ions will be behaving as diamagnetic ions. Next comes the color. The lanthanoid ions have unpaired electrons in their 4f orbitals. Thus these ions, they will absorb visible region of light and will undergo FF transition and hence exhibit color. Like in transition elements, we have seen that there is GD transition, and that is only responsible for the particular transition ions to become colored. And similarly here also the transition will be FF transition, and hence because of the presence of unpaired electrons in the 4f orbitals, the lanthanide ions show colored. Then the color exhibited depends upon the number of unpaired electrons in the 4f orbitals. Yes. Now what color will be exhibited or how intense will be the color, that depends upon the number of unpaired electrons in the 4f orbitals. The ions often with 4Fn configuration have similar color to those having 4F14-N configuration. Now lanthanide ions having 4F0, that means there is no electron in the f orbital, and 4F14, that is the f orbital is completely filled, will be colorless. Okay. Then lanthanide contraction we will see. This is a very important part. Contraction means what? There will be a decrease in size, progressive decrease in size with the increasing atomic number in the lanthanide series. So let us see. In the lanthanide series, with increasing atomic number, there is a progressive decrease in the size from lanthanum to lutetium, or from La plus 3 to Lu plus 3. This contraction size is known as lanthanide contraction. The general electronic configuration of these elements is 4f 1 to 14, 5s2, 66, then 5p6, 5d0 to 1, and 6s2. In these elements, the added electrons, they will enter the deep-seated f orbitals, and therefore they will experience a considerable pull by the nucleus. Due to very poor shielding of n-2f electrons, they exert a very little screening effect on the outermost 6s2 electrons. So due to this poor shielding effect of this n-2f electrons, we will see the screening effect will be in very little or very less on the outermost 6s2 electron. Hence, with the increasing atomic number, the enhanced nuclear charge leads to contraction in the size of the atoms or ions. So this is what is lanthanide contraction. Now applications of lanthanide contraction. This can be actually consequences also. So here first we will see atomic size. So what is the impact? The ionic radii of zirconium plus 4 is about 9%, and that of more than that of Ti 4 plus. Okay. So here you see similar trend is not maintained on passing from the second to the third transition series. The ionic radius of hafnium plus 4, instead of increasing because of the inclusion of one more electron shell, it decreases as a consequence of lanthanide contraction. That means it tells us about the progressive decrease in size among the elements of the lanthanide series. And next, this explains the close similarities between the members of the second and the third transition series than between the members of the first and the second transition series. So due to these lanthanide contraction, we will see that there will be close similarities between the member of the second and the third transition series, and then between the elements of the first and the second. Okay. So second and third, there will be similarity compared to the first and the second. As we know that there are 4 transition series, 3D, 4D, 5D and 6D. So 5D and 6D, there we will find the lanthanoids and the actinoids. Okay, in between. Then basic nature of hydroxide, you see. The effect of lanthanide contraction, basic nature of hydroxide regularly decreases. Okay. And all is happening because of the lanthanide contraction only. Similarity in the properties of lanthanoids. Due to small difference in the size, the chemical properties of lanthanoids are similar, and hence their separation is difficult. Okay. So because of the presence of lanthanide contraction, we will see that the chemical properties of lanthanoids will be similar, and hence the separation becomes very difficult. And this is a small decrease in size or small difference in the size is actually also one of the reasons behind the lanthanide contraction. Then this is the important reaction of lanthanoids. You see, Lanthanides reacts with carbon at 2773 Kelvin to form LnC2. This Ln refers to the lanthanoids. Then with water it forms hydroxides, with halogens it forms halides of the lanthanides, with acids it gives off H2 gas, and it burns in the presence of O2 giving you Ln2O3. Then in case of when it is heated with sulfur we will get here Ln2S3, and when it is heated with nitrogen we will get the Ln means lanthanide, any of the elements of lanthanide with the nitrogen. That means the formula will be Ln. Now here niche metal, very important thing, this is an alloy of lanthanoids, mainly cerium and iron. Okay, so this is about the lanthanoid series. So in lanthanoid series you need to know its physical properties first, then you need to know what is lanthanide contraction and what are the consequences of lanthanide contraction, what happens to the change in atomic size, the hydroxides, okay, the properties of the different elements because of the lanthanoid contraction. So these are all the consequences of lanthanide contraction. Next we will start actinoids. So in actinoids you see this is the 5s series, so that was the 4s series. So the elements in which the extra electron enters the 5 orbital are known as actinoids. So here the extra electron will be entering the 5s orbital, but in case of lanthanoids we saw that it will enter in the 4s orbital. Okay. Then the man-made 11 elements, okay, from Np to Lw are placed beyond uranium in the periodic table and are collectively called transuranium elements. Okay, so these 11 elements, they are placed beyond uranium and hence are known as transuranium elements. Then Th, Pa and U, these are the first 3 actinoids and are natural elements. Okay, then electronic configuration you see, please keep in mind the difference with the lanthanoids also. The general configuration of actinoids may be given as Rn, 5s1 to 14, 6d012 and 7s2. Now oxidation states you see, remember the oxidation states what we have learned in lanthanoids was what? +2, +3 and +4. Over and above there were no other oxidation states, of which we found that in lanthanoids +3 oxidation state was common. But let us see in actinoids. In lanthanoids and actinoids, +3 oxidation state is the most common for both the series of the elements. So here also in actinoids we will find that all the elements of the actinoid series will have +3 oxidation state. Now the oxidation state becomes increasingly more stable as the atomic number increases in the actinide series. So here the stability of oxidation number will be increasing as the atomic number increases. Okay, and they will become more stable with the increase in the atomic number. Okay, then highest oxidation states in the actinoids is +7, which is exhibited by Np and Pu. Np with atomic number 93, Pu with atomic number 94, it is unstable. Okay, so the maximum oxidation state which is exhibited by the lanthanoid was +4, but in case of actinoids we see that it is +7 and it is exhibited by Np and Pu, which is highly unstable. Then highest stable oxidation state is +6, which is shown by uranium 92. Okay, then other properties let us see. Physical appearance, actinides are silvery white metals. They get tarnished when exposed to the attack of alkalis. So when they are exposed to alkalis, they get tarnished. Okay, then that means they get corroded. Okay, or corrosion takes place. Then density you see, all the actinoids except thorium and americium have high density. Okay. Then color, actinide ions are generally colored. The color of actinide depends upon the number of 5f electrons. So the ions containing no unpaired 5f electrons or exactly full-filled 5f shell are colorless, as usual in case of 4f. We saw that 4f0 and 4f40, they were colorless because there were no unpaired electrons in the 4f orbital. Similarly, same case is here, but the case here will be for 5s orbital. Ionization energy value of actinoids are low. Okay, so they will have low ionization energy. Then all the actinide metals are highly electropositive. They resemble lanthanide series in this respect. That means lanthanides as well as actinoids, they are metals and they are highly electropositive. Then melting and boiling properties, they have high melting and boiling points. They do not follow regular gradation of melting and boiling points with increase in atomic number. So here they will have high melting and boiling points, but there is no any gradual increase in the gradation in the boiling points and melting points with the increase in atomic number. Then magnetic properties, the actinide elements are paramagnetic due to the presence of unpaired electrons. Radioactive nature, all the actinoids are radioactive in nature. So see, when we learn the properties of the lanthanoids and actinoids, we can easily sort out some common differences between them as well as some common points also between them. Now here you see actinide contraction. Like lanthanide contraction, we have actinide contraction also. So the size of atom or cation decrease regularly along the actinide series. The decrease in ionic radii with the increase in atomic number is referred to as actinide contraction. This is due to poor shielding of 5s electrons. So in case of lanthanide also, we have found that there will be a progressive decrease in the ionic radii with the increasing in atomic radius. So that was lanthanide contraction, and that is also due to the poor shielding of 4s electrons. But in actinide contraction, it is due to the poor shielding of 5s electrons. You try to remember like this. Then comparison of lanthanoids and actinoids. Now you see here it will be divided into two. One is what is the point of resemblances between them. Another will be what is the point of differences or distinction between them. So let us first see what are the points of resemblance. Both lanthanoids and actinoids show a dominant oxidation state of class 3. Yes, when we went through the properties, we saw that the common oxidation state for lanthanoids and actinoids is class 3. Then we saw that both are electropositive and act as strong reducing agents. Yes, those metals, they are generally electropositive, and these lanthanoids and actinoids, they are highly electropositive and they act as good reducing agents. Then cations with unpaired electrons of both of them are paramagnetic. Yes, those ions which will have unpaired electrons in the 4f or the 5f orbitals will show paramagnetic character. So this is seen in case of lanthanoids as well as in case of actinoids. Most of the cations of lanthanoids and actinoids are colored. Yes. Then both of them show a steady decrease in their ionic radii along with the series. Yes. In both of them there will be a decrease in the atomic radii along the series, which is due to poor shielding effect. One may be named as lanthanide contraction since it is for the elements of the lanthanoids or lanthanide series. The other is actinide contraction for the elements of the actinide series. Now let us sort out what are the points of distinction between them. Lanthanoids. Besides the most common oxidation state of class 3, lanthanoids show class 2 and class 4 oxidation states in case of certain elements. Yes, they have common oxidation state as class 3, but over and above that they have class 2 and class 4 as the common oxidation state. Now in case of actinoids, besides the most common oxidation state of class 3, actinoids also show class 4, class 5 and class 6 oxidation states in certain elements. Then lanthanoids have less tendency towards complex formation. Yes, lanthanoids do not have a good tendency to form the complexes, but actinoids have a stronger tendency towards complex formation. Then in case of lanthanoids, except promethium, they are non-radioactive, but in case of actinoids, all the elements are radioactive. And then in case of lanthanoids, oxides and hydroxides of lanthanoids are less basic. Okay, but in case of actinoids, oxides and hydroxides of actinoids are more basic. You do one thing, no? When you see this one, this more basic will come to the block of actinoids. Okay, so in case of lanthanoids, oxides and hydroxides of lanthanoids are less basic, but in case of oxides and hydroxides of actinoids, they are more basic. This more basic should be shifted here. Okay. Then some important uses of actinoids are as follows. Thorium is used in atomic reactors as fuel rod and also in the treatment of cancer. Uranium is used as a nuclear fuel. Its salts are used in glass industry for imparting green color, textile industry, and also in medicine. Plutonium is used as a fuel for atomic reactors as well as in atomic bombs. So these are the characteristics, you can say, of the elements belonging to the Lanthanide series and the Actinide series. Okay. So from here sometimes the resemblances come, this year the differences came. Okay. And sometimes you may get some reasoning based questions related to its magnetic properties and color, and sometimes even to its the formation of hydroxides also. Okay, which is one of the application of Lanthanide contraction, basic nature of hydroxide. Okay, so students, you can please prepare the note from here. Okay, and this actually I gave, you can see it in the periodic table, in the big periodic table also, which where you will find out the inner transition elements at the bottom of the periodic table. Okay, so please remember in the lanthanides as well as in the actinoids, which are the elements which will have 4f7 electrons in their orbital, or which will have completely filled electrons in the 4f orbital in case of lanthanoids, and in case of actinoids also. You need to remember the names along with the symbols. Okay, if you go through the characteristic properties, it will be very easy to remember. Okay, so please go through it, and also go through the PPT which I will be sending to you along with this, and then in your free time please prepare a good note on it. Go through both this one also and the PPT also. That will help to understand it in a very better way. And some things which you may find it difficult here, maybe the PPT is given in more easy language, so you will be able to understand there also. Okay, so please prepare the note. That's all for today. Thank you and have a nice day. God bless you.